Hi everyone, this is Kalyan Kumar and welcome once again to the 11th episode of Gaseous State. So far we have done ideal gases. We had started with understanding what is a barometer, what is a manometer, and we have come a long way. We have finished 10 episodes and we have finished ideal gases. And now it's time to turn to real gases, the gases that actually are. Now the most important part about this particular video is that I'm going to explain to you what is a real gas and what is the equation that works mostly at a pretty good range of temperature and pressure for a real gas. Remember, there is not a single equation that works for all gases at all range of temperature and pressures. There is simply not one. There is no unified gas equation. In fact, if I remember correctly, there are around 25 gas equations which are meant for real gases at different range of temperature and pressures, and that too for gases of certain groups. The ones which have van der Waals forces, the one which have hydrogen bonding, you have different equations for them. And the equation which works the best for most of the gases at a very large temperature and pressure range is what we are going to discuss in this particular video. So there is still a dearth of a real gas that works, a real gas equation that works at all range of temperature and pressure, and that too for all gases. Besides that, not only are these people wizards in trying to figure out such a gas equation, but the best part about it is how they figured out this gas equation. For example, if it were left for you or me to find out an equation of state for a real gas, we'll take a particular gas, we'll do some experiments on that gas, and we'll try to write a gas equation. And the worst part is that that gas equation will only work for that gas, and that too for the range of temperature and pressure in which we have done the experiment. But imagine that we do not do any experiment, we use the ideal gas equation, and using that we figure out the equation of state of a real gas. Now that remarkable feat was achieved by van der Waals, and it is therefore known as the van der Waals equation of state. And not only should we appreciate the fact that he is able to get an equation for a real gas, he was able to get the equation of a real gas without doing an actual experiment. Though the ideal gas equation itself was based on experiment, but this particular equation of state was purely theoretical. And what he did basically was he took out two assumptions from the kinetic gas equation. If you remember the kinetic gas equation, we talked about a molecule to be a point mass. We talked about that a molecule doesn't possess any volume of its own, and that there are no intermolecular or interatomic forces existing in gas molecules, which is the reason they are able to follow, all of them are able to follow the same equation of state. But here, we are going to do away with those two assumptions, and in spite of that, we will derive the equation, or rather van der Waals was able to derive the equation completely theoretically. So here it goes. So let's understand how a real gas is going to work. There are, as I said, about 25 different gas equations, none of which work at all range of temperature and pressure, and that too for all type of gases. And one of the most relevant gas equations for real gases is the van der Waals equation of state, which looks like this. P plus an square by v square multiplied by v minus nb is nRT. Now this equation has been theoretically derived by a thought experiment in which a real gas is converted to an ideal gas, and then writing the ideal gas equation using the parameters of real gas. Now here again you need to understand this. What he basically did was, he took a real gas and used the pressure and volume exerted by the real gas and occupied by the real gas, and converted in his mind it to be an ideal gas. And whatever changes he had to make in the pressure and in the volume, he made those changes, keeping the pressure of the real gas and keeping the volume of the real gas. He made those changes, and then he wrote the ideal gas equation. So he said that if a real gas is exerting this pressure, what is the ideal gas going to exert? If a real gas is occupying this volume, what is the ideal gas going to occupy? And then knowing the pressure of the ideal gas and the volume of ideal gas, using the pressure and volume of the real gas, he was able to write the ideal gas equation, which effectively connected the pressure, volume, temperature and number of mole of the real gas. So there are two assumptions of kinetic gas equation. The Van der Waal rectified in his equation. One of them is the size of the gas molecules and the second is the molecular interaction. And these corrections are known as volume correction and pressure correction. So let's start with the volume correction. Now imagine n mole of a real gas in a container of volume V. Let us assume now that the real gas molecules have a certain molecular size that cannot be ignored. Let this be the container and all of these are molecules. As you can see now, they are not point masses. They're already having a real molecular size. Of course, we still make the assumption that they are hard spheres. Let the volume blocked by 1 mole of molecules be B. Now this is again something that you need to understand. I'm using the volume blocked by n mole of molecules and I'm keeping that as B. Now one might argue, one might want to know, what do you mean by volume blocked? Well, first of all, the volume of an ideal gas is basically the volume available in space where the real gas can move. So that would exclude the volume which the molecules themselves are possessing. But rather than calling the volume occupied by the real gas, 1 mole of real gas is B, I'm assuming the volume blocked by 1 mole of molecule is B. And very soon you'll understand why I'm using the word blocked and not occupied. Now let us assume that the volume blocked by the molecules is reduced from the volume of the vessel and the molecules are considered now as point masses. This would look like an ideal gas now. Now again, this is something which you need to understand. If a real gas is in a container V and it has considerable volume of its own, then you can assume that the container is not V, it is V minus the volume of these molecules, or assume that the volume which these molecules are blocking be a part of the vessel itself, maybe the thickness of the sides. So if B is the volume blocked by 1 mole of molecules, then obviously NB will be the volume blocked by n mole of molecules. So rather than assuming that the molecules have molecular size, let's assume that the container's edges are that much thick, which means the volume available inside is reduced, and now you can consider the molecule to be point masses. Try and understand this. The volume blocked by n mole of molecules is NB, but rather than they taking that as NB, I'm assuming that the container itself is blocking the volume NB because of its thickness, and inside now you only have point masses molecules, which therefore becomes an ideal gas. So what is the container's volume for the ideal gas? It is V minus NB. However, the volume of the vessel containing the ideal gas is now V minus NB. So the ideal volume is the real volume minus NB. So likewise, I'm going to look at the pressure now. Now it talks about pressure correction. The pressure correction works like this. Pressure exerted is the force applied per unit area by the molecules of the gas on the wall of the container. This force is applied by that layer of molecules that are closest to the wall. So assume this is the container and I'm showing this in a 2D, and assume that these molecules which are very close to the side of the container are the ones which are exerting the pressure. And there is a layer that is behind this layer which is attracting this layer due to intermolecular forces. So remember, another assumption that we are doing away is that the intermolecular forces are zero, because when they are considerable, then we cannot assume them to be zero. So let's assume this is the layer which is right behind the layer attacking the sides of the container. Let this layer be attracting that layer, and there are intermolecular forces. Now, because of the backward pull of the second layer, the first layer exerts pressure lower than the pressure of the ideal gas. Now what you need to understand is, if the pressure of the real gas is P, this P is taking into account the pull of the second layer on the first layer. Had there been no pull, can you see the pressure that is exerted by the layer closest to the wall would have been greater? So don't you think that the real gas pressure is lower than what the pressure would have been had the same mole of ideal gas been there? If the pressure exerted by the real gas is P real, then the pressure which the ideal gas would have exerted would have been slightly more than this, where small p denotes the pressure loss of the real gas due to attractive forces. We will assume that the force between only successive layers are significant. So in our assumption, we are only assuming that layer 1 is attracted by layer 2. Layer 2 is attracted by layer 3 and layer 1. But we are not using the attraction of layer 1 because of layer 3. And that assumption can definitely be made. As it is in ideal gas, you have made the assumption that there are no force of attraction at all. And here at least you are considering the attraction between two successive layers. So P ideal becomes capital P real plus small p. And the pressure lost due to attraction should then be directly proportional to the extent of attraction between the two layers. The force of attraction should be directly proportional to the concentration of molecules in the layer closest to the wall as well as that in the layer behind this. Now this is where I want you to understand something. So now the force between two charges, the Coulombic force between two charges is what? F equals K Q1 Q2 upon R square, right? What is the force due to gravitational attraction between two masses? It is G M1 into M2 by R square. Now my first question to you is, why do you think we are multiplying the two charges? Why are we multiplying the two masses? Why aren't we adding them? Or why isn't there any other symbol in between them? Why it is Q1 into Q2? Now I want you to pause the video and think about this for a little while. Why are we multiplying these two? Now of course in charges you might say that if I add the two charges, the sum will become 0 if they are opposite charges. How about mod Q1 and plus mod Q2? What is wrong with the plus sign? Now I'm not asking you to prove this. It is beyond proof. It is proved. This is proved. If you double Q1, force becomes double. It's proved. You double M1, the force becomes double. It's proved. So why is it that the nature has built the force in such a way that the charges have to be multiplied, the masses have to be multiplied? Because remember, the force is proportional to both. Meaning, for this force to exist, you need Q1 and Q2. If it were Q1 or Q2, you would have had an addition sign. So, and condition is always multiplication. Or condition is addition. Why? Because if even one of them is 0, the force cannot exist. For the force to exist, you need both to be present, both to be non-zero, which is why I am calling it AND. But if it were Q1 plus Q2, even if one is 0, the other can keep the force on. So multiplication is OR. You don't need both. You can even do it with one. But to make sure that you need both at the same time, you have an AND condition. Similarly, the pressure which is lost due to attraction, which pressure of course is directly proportional to force, is proportional to the concentration of the molecules which are hitting the wall. Because remember, if because of attraction between two molecules, the force is reduced by, let's say, 0.01 bar, then the attraction between two molecules will reduce it by double of that. Attraction between three molecules will reduce by triple of that. So it is proportional to concentration. So it is proportional to the concentration of the layer which is hitting the wall, as well as proportional to the concentration of the one which is behind it, behind that layer attracting it. Q1 and Q2. You need the concentration of both. Therefore, the pressure loss is directly proportional to N square by V square, and the proportionality constant is what we call it as A, where A, because now this A is dependent on the gas. Because remember, when we are deriving van der Waals equation, it has to work for real gas, and all gases being different, there has to be some characteristics of different gases which have to be different. Try and understand this. If there is a gas with a different A, I will have a different equation. But the generalized equation will use A. The value of A can differ for different gases. And what does the value of A represent? The value of A says that if I have ammonia and hydrogen, both having the same concentration, they will not suffer the same pressure loss due to attraction. Because hydrogen only attracts by van der Waals forces. Whereas ammonia also attracts by hydrogen bonding. So the A value for both will differ. So not only is the concentration of the two layers important, also the nature of the gas is important. So the A value will take care of that nature of the gas. Similarly, the B value takes of the nature of the gas because the volume blocked by molecules will be different for different gases. A denotes the proportionality constant and it denotes the attraction based on the nature of the molecules. It is defined as the pressure loss due to attraction for 1 unit concentration of gas. So if N by V were 1, then the pressure loss would be simply A. Higher the A value, higher is the attraction between gas molecules. So you can clearly see ammonia will have a greater A than gases which attract only by van der Waals forces. And polar molecules will definitely have a higher A than non-polar molecules. So what does the equation look like now? P ideal into V ideal is nRT. So what is the P ideal? P ideal is P real plus A n square by V square. V ideal is V real minus NB equal to nRT. Look at how beautifully, amazingly beautifully, van der Waals was able to get the value, the equation for the state of a real gas without doing an experiment, just by doing a thought experiment. Now let's talk about the van der Waals constant B. Now the van der Waals constant B, this is something which is again pretty unique. On one hand, we say, remember I said it is the volume blocked and not the one occupied, because it turns out that the volume blocked by one molecule is 4 times its own size. Now this is not intuitive. This looks absurd. Shouldn't the volume blocked by a molecule be its own volume? No, it's 4 times that. Why? Because the molecules are, number one, are not static, they're constantly moving. Secondly, the molecules are always in collision. So let's figure out why is B 4 times the volume of 1 mole of a gas. The van der Waals constant B is defined as the volume blocked by 1 mole of molecules. It is given as B equal to 4 into volume occupied by 1 mole of molecules, or 4 into 4 by 3 pi r cube, which is the volume of a sphere, into the Avogadro's number. Now if gas molecules had not been colliding with each other, then B would have been simply equal to the volume occupied by 1 mole of molecules, which is what I said. But molecules are constantly colliding with each other. And the probability of a molecule in collision is far greater than its probability of not being in collision at any given moment of time. So, to understand this, what we're going to do is we are going to look at collisions. But the problem is, molecule 1 can collide with almost all the molecules of the system. It is going to be very difficult for us to look at all the molecules of the system in one go. So we are going to make some assumptions. But for every assumption we make, we get into a problem, and therefore we make some more assumptions till all the assumptions seem to help us get to the closer to the truth. Remember, approximation to the truth. So we are going to make assumption 1, we will find that because of that there is something else that is happening, there is some other problem, we will take care of that by making another assumption, that will lead to another problem, and so on till we are able to solve all the problems. So to make the system look simplistic, we make the following assumptions. All molecules keep colliding with one another, so much so that we assume that every molecule is always in collision. Now, the moment a molecule becomes free from a collision, there is another molecule with which it will collide almost in the very next moment. So, if 2 molecules collide like this, the moment they are apart, there is another one just behind it to collide with it. Therefore, there is absolutely no moment when it is not in collision. We are going to remove all the moments of not collision, which in fact in the real situation will happen. But then remember, we cannot deal with the real situation the way it really is. Though we are talking about real gases, but we are going to make sufficient number of assumptions to make things, at least we'll be able to derive them. And remember, science is about not the truth, the approaching of the truth, the approximation that leads us very close to the truth. So all collisions are bimolecular. This again is another assumption. Need not be three molecules can collide at one moment. But remember, as we discussed before, the probability of that happening is very low. Since all molecules of a gas are similar, we will focus our attention only on one pair of molecules. So to make the system simpler, to be able to understand, we know that 1 and 2 collide, then 1 and 3 collides, then 2 and 5 collide, then 3 and 4 collide. All of these things will happen. But since all molecules are similar, we will assume only 2 molecules. We will just make the molecules as pairs. 1 collides with 2, 3 collides with 4, 5 collides with 6, and so on. Now, in making these pairs, there is one problem. What happens if there is an odd number? But remember, we can eliminate that one molecule. One molecule is not going to be making any difference to anything that is calculatable. We're not going into that many decimal places anyway. So, to ensure that we don't have to consider all the molecules, we will assume that each molecule chooses its partner and collides only with its partner. This way we get to look only at 2 molecules at a given moment of time. But with this assumption, the problem that will arise would be that there would be equal moments of no collision. As soon as a molecule disengages from its partner, it would spend a moment without being in collision before it collides again with its partner. So just try to understand. We are saying, okay, 1 and 2 collide. But if 1 and 2 collide and one has chosen its partner as 2, then what happens when it moves off? Since it will only collide with 2, now there is a moment when it is not in collision. Again collision, not in collision. So remember, we already made the assumption that there is no moment of time when it is not in collision. So how do we take care of this problem? Simple. We assume 1 and 2 are stuck to each other. 1 and 2 are stuck to each other, 3 and 4 are stuck to each other, which means they are always in contact with another molecule, which is going to simulate the fact that it is going to collide in all directions, in all moments. But again, this gives us another problem. If 1 is stuck to 2, they will remain as it is. But remember, a collision can happen like this, it can happen like this, it can happen like this. To simulate a real environment, we need to look at all directions of collisions. So how do we solve this? Simple. We say the 2 molecules are stuck to each other and they rotate. They rotate in all possible directions. To take care of this, we will assume that the molecule and its partner are stuck to each other always. But this assumption would cause another problem. If a molecule is stuck to its partner, then it cannot collide with all possible manners. To take care of this, we assume that a molecule and its partner are stuck and they occupy various positions at various moments in space about a common point of contact. Now look at a fan. A fan has a center, a circular center, and it has got 3 wings. And let's assume that the area of the circular thing and the 3 wings totally adds up to 10 meters square. And let's assume that the cross section of the room area is 100 meters square. The area physically occupied by the fan is 10 meters square in that layer. Does it mean I can put 10 fans in the room? No. A fan is not meant as an ornament. A fan is supposed to move. So can you see that even though it is only occupying 10 meters square at any given moment, but when it rotates, can you see it blocks a certain area? So you cannot have any other fan in that area, which means you don't want any other wing to project into that area. But even when it is rotating at any given instant of time, it is only occupying 10. But it is blocking far greater than 10. So when a molecule is stuck to its partner and is rotating in all possible manners, at any given point of time, it is only occupying the volume of 2 molecules. But remember, it is blocking far greater than that. Which is why I use the word block and not occupied, because whatever is its own volume, it blocks far greater than that. So if I were to take 2 molecules like this, at one moment they are like this, the next moment they are like this, the next moment they are like this, the next moment they are like this, then they are like this, then they are like this. So can you see that the volume that they are blocking is the volume of this sphere? And can you see the volume of the radius of the red sphere is the diameter of the smaller one, or 2 times the radius of the smaller one? So what is the volume that is blocked? The volume that these two rotating molecules will block will be the volume of a sphere whose radius is 2r, where r is the radius of one molecule. So what is the volume blocked by these two molecules? It is 4 by 3 pi 2r cube, which is 8 into 4 by 3 pi r cube. So if two molecules block 8 times the volume of one small one, what is the volume blocked by one? Half of this, which is 4 times the volume occupied by one small molecule. So the volume blocked by one molecule is 4 into 4 by 3 pi r cube. So B becomes 4 into 4 by 3 pi r cube into Na. So that brings us to the end of this video. It's a very short video, and I hope you were able to understand what I wanted to convey in this particular video. And if required, go through this video as many times as you want to understand every part of this video. And if there is anything that you haven't followed, any suggestions that you have, any comments that you want to make, please drop all of them in the comment section below. If this video was useful to you, do hit the thumbs up button and check out the other videos of this channel. You'll find lots of chemistry videos, you'll find a lot of animation videos, SN1, SN2, a lot of organic videos. So check out all those videos, and if you find them to be useful to you, find them to be useful to your course, do subscribe to this channel. You'll find more and more and more videos getting uploaded in this, and therefore hit the bell icon too, so that you can be notified right at the moment when the video is uploaded. With that, this is Kalyan Kumar signing off. Have a wonderful day. Goodbye. Thank you for watching this, and see you till the next one.